All right, please take it away.
Yeah, so welcome everyone to the final installation in our series on the Weil conjectures. We've come a long way um, from the humble beginnings of talking about classical questions in number theory, primes, and things relating to the work of Riemann on the zeta function, all the way through to some varieties of the finite fields, and maybe even some proofs and hints of what the techniques might be in general. So, on that note, we did start with the classical Riemann zeta function, the sum of 1 over n to the s. This series, as written, is defined for any complex s with real part greater than 1. But then you have this thing, which we refer to as our Riemann package, which has a lot of great data in it. It includes ideas like, well, this function actually can be analytically continued to a large domain. There's a functional equation that relates the values for real part s greater than 1 to those when you flip it. We also have the big thing, the Riemann hypothesis, which is telling us about the zeros of this function. And that's a big open question, which we don't have a lot of progress on. Still lots of things that people are trying to do. People have approached it in different ways. Some people like making some sort of analytic arguments showing that, well, the zeros have to lie maybe within a certain region or there are certain bounds on their size. Other people try and put things into a framework where maybe we can use other techniques to access this question. One framework that people like is the framework of geometry. And in geometry, we have analogs of the Riemann zeta function coming from varieties of a finite field. So as a reminder, given a projective variety over a finite field, fq say, the zeta function of that variety, x, now a function of t, is the exponential of this particular power series. So it's sort of a generating function for the point counts, and then you exponentiate that, and this gives you an interesting function. And I basically always work with this as a function of t, but if you want to make the analogy tighter between the zeta functions in this world and the zeta function classically, then the transformation you want to make is replace t with q to the negative s. So q is this cardinality of the base field, and then s is your new variable. So just make a substitution, t equals q to the negative s, and suddenly these two things will look a lot more similar. But for us, we'll just basically always work with these functions of t, because it turns out it's nice enough in this setting to view them that way. This is actually one of the reasons why the setting is so nice. We, again, for these sorts of zeta functions, had something we called a Riemann package, and that got the name in the setting of the Weil conjectures. So as a reminder, what were the Weil conjectures for this particular function, this exponential of a power series? Well, the first thing is that this rather complicated looking thing was actually a rational function. It was just a quotient of polynomials. And in particular, we could say those polynomials factored over the integers into a certain number of factors, where this d appearing here is the dimension of the variety x. So if x is, for instance, a curve, I'm missing it. There should be a p0 on the bottom, actually. That's a missing piece here. One of these should be p0. If x is a curve, we would expect to get a p0, a p1, and a p2. So it's one-dimensional. But for high dimensional things, we expect something like this. These are all integer coefficient polynomials. And this rational function satisfies a functional equation. So again, this is not dissimilar to what we know of the Riemann zeta function. If we make some substitution here, which if you use this change of variables, t equals q to the negative s, this is analogous to just shifting s or doing some reflection in s, then we get the same thing back with some sort of fudge factors at the front. Again, exactly the same sort of thing that we expect for the Riemann zeta function. In this case, the fudge factors are a power of t and a power of q. And the powers that we get are determined by the dimension and this quantity chi, the Euler characteristic, which we actually haven't defined yet, but there is some quantity called the Euler characteristic associated to a variety that you can calculate and gives you this formula. And then perhaps the biggest piece of the Weil conjectures, number 3, is that if you actually factor these integer coefficient polynomials over the complex numbers, look at their complex roots, they all have this form. They are all of the same absolute value, precisely q to the I over 2. This is what we call the Riemann hypothesis, because, again, with the change of variables t equals q to the negative s, we're kind of saying something about the zeros of this. When does this vanish? Well, this vanishes when wij times t equals 1. And so, if wij in size is the power of q, then t will have to be its inverse. So t will also have to be this appropriate power of q. So if we've made a substitution, t equals q to the negative s, we're basically saying at what values of s does this vanish? So that's why this gets called the Riemann hypothesis. Describing the size of this wij is very close to saying the vanishing of this function if you make the substitution t equals q to the negative s. And then finally, there was a sort of nice relationship between this expression and expression about the Betti numbers of a variety. So if our variety over the finite field was actually the reduction mod p of something living over a field of characteristics 0, then in the field of characteristics 0, we can compute the Betti numbers, which are calculated via certain cohomology groups, which we'll actually talk a little bit more about today. And then these groups are abelian groups. We can calculate their rank, and those ranks are called the Betti numbers. And these Betti numbers should precisely equal the degrees of these polynomials. So there's a relationship between the degrees of these polynomials and these abelian groups, these cohomology groups associated to something. So that's the Weil conjectures. And when we introduce these, we first began with an example, a very classical example being the zeta function of projective space. We in fact started with the projective line P1. P1, sometimes we think of as A1, just normal, the normal line, plus a point at infinity. So if I have a line, a one-dimensional thing of f q to the n, then that should have q to the n points plus the 1 point at infinity because we're projective now. And if you just plug this directly into that power series expression, take the exponential, and you'll get this. The power series itself will basically look like some logarithms, and then the exponential cancels out, and that's what gives you this rational function. So that's the zeta function of P1. And we can do something in higher dimension. So you can build d-dimensional space in sort of inductively out of affine spaces if you like. It's one way to see this formula. Or you can just write down what the definition is and calculate, okay, well, it sort of lives in like d plus 1 dimensional space, but they're not allowed to be 0. But then you mod out by non-zero scalars. So you sort of get q to the d minus 1 over q minus 1. So you get an expression like this. But that's what we expect out of our d-dimensional space. And once again, this just works out really nicely. Basically, if the point count is a sum, because we're exponentiating, we kind of expect this to just factor as a product. And so it factors exactly into this nice list of terms. 1 minus t, 1 minus qt, dotted up to 1 minus q to the d t. And again, these can be rewritten as functions of s. So q to the negative s, q1 minus s, if you like. So that's the zeta function of projective space. A nice example that you can just write out very explicitly. For a first, maybe sort of non-trivial class of examples, we talked about elliptic curves. So we started doing these by using Sage to do some point counting. Now, this point counting you can obviously do by hand, as was sort of, as was done by the ancients, as it were. But we have things like Sage now, so we can do that. And I think if you've been following along this seminar series and some things have sat well with you, some things have been unclear, if one takeaway you have is Sage is cool and good, then that's a great takeaway. You can do a lot with it, and you can do all sorts of fun calculations and see interesting patterns lead to further realization. So highly recommend playing around with any of these examples yourself and getting a feeling for them, counting points and seeing what patterns arise. But when we did that ourselves, we used Sage and we did some point counting, and we got that they always came out to look like this. The zeta function of an elliptic curve is 1 minus aqt plus qt squared with these two terms in the denominator, 1 minus t and 1 minus qt. So as we said, this is first of all what we expect for a curve. It's got the 1 minus t would be our p0. This numerator is our P1 and this 1 minus QT is our P2. So that works. And this AQ number is sort of the only thing that changes. You change the elliptic curve. The zeta functions of different elliptic curves. The only difference between them is this one quantity here. And that quantity is calculated by taking 1 plus Q minus the point count of the elliptic curve. Sometimes people call this sort of the error term because we sort of gave a heuristic why the point count should sort of approximately be 1 plus Q. And then AQ is measuring how far away you are from that. And so there was some interest in how bad this error term can be. And Husser was the first to give a proof that AQ is not so large. It is in fact smaller than 2 root Q. It's the Husser bound. And we saw how that bound is enough to show that this numerator factor has roots of the correct absolute value. So we were able to prove the Riemann hypothesis using Husser's theorem. We gave a full proof of all of the Weil conjectures for this case. We sort of described how everything works for the rationality, for the functional equation, and indeed the Riemann hypothesis. But we used some more modern tool out of Silverman's book. And one thing I want to note about this is that you get a huge amount of sort of information just implicitly by knowing this zeta function. Like, for instance, as I mentioned, if I have 2 different elliptic curves, the only difference in the zeta functions is this one quantity AQ. Once you know the AQ value, which is determined by knowing the point count over the base field, you know the whole zeta function. But the zeta function has the information of every single point count in it. So, corollary, if I know the number of points over FQ on this elliptic curve, I know the number of points over every finite field extension of that. I know every FQ to the n. I can count the number of points just by knowing the number of points over the base field. That might not tell me what the points are exactly, but I know how many there are at least for every single value of n. And one question I'd like to sort of give you all to ruminate on is, well, if I know all the point counts, to what extent do I just know the elliptic curve? Another question is, if 2 elliptic curves have the same zeta function, is there a relationship between those curves? Are they isomorphic? Is there a map between them? What do we have? So that's an interesting question to consider. 2 elliptic curves over a finite field with the same zeta function, what is the relation between them? Okay, so let's just remind ourselves of how the proof for this one went. Just generally, what were the sort of the tools, the key inputs that we used? So the first key input was that we had E had some associated vector space. Actually, we used a free module, but you can just sort of invert. It was a module over the L-adic integers. You can just invert L and get a QL vector space. And that will be sufficient for proving the Weil conjectures. It's worth noting that these aren't equivalent data. Knowing this module is like knowing a lattice inside this vector space, so it's a little bit more data. But for the purpose of proving the Weil conjectures, either one of these 2 pieces of information will do. And the interesting thing is that you have to pick some prime L away from Q, but the actual choice of prime doesn't matter. Every different L, as long as it's not equal to Q, would work. So it's funny that you have to pick an auxiliary prime, but which one you pick doesn't actually change anything. So that was one thing we needed. We need to know that there was some vector space that we could work with, so we could make a sort of linear algebra problem. We then need to know that if I had some sort of endomorphism of my elliptic curve, that would induce some operator on this linear algebra object, on this vector space. So maps on E turn into vector space maps on this L-adic Tate module. That was really important. And specifically, we were able to deduce a relationship between the size, the number of points of E over a particular field, so with the point count that we need to define our zeta function, and we were able to relate that to the trace of an operator acting on this vector space. So that was key. And finally, one thing that was actually very important, although it only appears sort of implicitly, was the existence of a Weil pairing. So we didn't actually sort of describe what this is or how one uses it, but we had this really key theorem when we were doing the elliptic curve case that we needed to say, oh, the degree of an endomorphism is related to the determinant of the associated operator. And I mentioned in passing that that theorem, which I didn't prove, relies on the Weil pairing. So there's some sort of very special pairing on our vector space, and that was actually secretly key. So here are some key things that were important for the elliptic curve case. So it's worth thinking about those and keep them in mind as we move to more general examples. So just what we want to attempt to do is wonder how one might generalize the proof of elliptic curves to other varieties. Before we do that, one more example. There'll be another curve, in fact. So, well, any other curve. Weil's original work was on studying various special curves like Fermat curves, hyperelliptic curves, which Masoud told us about. And in general, if I take any projective curve, there's an invariant of that curve called the genus of the curve. The projective line is a curve, it's a one-dimensional space, and its genus is 0. An elliptic curve has genus 1. This is related to the fact that when you look at a characteristic 0 elliptic curve, when you look at its complex points, you get a torus. So it has genus 1 in that sense as well. So this is definitely a related thing. But the genus is just some invariant of the curve. And in fact, the genus will determine the shape of the zeta function. So elliptic curves all have a particular looking zeta function. They have some quadratic in the numerator and in the denominator. For a curve of genus G, then the zeta function has this general shape. So it has the 1 minus t and 1 minus qt denominator. That's not going anywhere. The numerator is some polynomial, but now its degree is 2 times g. So at the very least, you can see that this specializes to what we have in the projective line case, where g equals 0, so the numerator is a constant, 1. And the elliptic curve case, g is 1, so we get a quadratic. But if I have a higher genus curve, I get a more complicated numerator. But I still only have one factor because it's still, curves are one-dimensional, so these are the only 3 factors of my zeta function. This case, so we mentioned that the previous case of the Weil conjectures was due to Hasse for elliptic curves. This case, the case of general curves, is due to Weil, and his proof used the theory of Jacobians. So given a curve, you can calculate something called its Jacobian. The Jacobian of a curve is another variety. It's an abelian variety. These typically are higher dimensional, so you might think, okay, well, that's going to be a harder thing to work with, but by being abelian varieties, that tells you they have a group structure. And you might remember that group structures were really important in the elliptic curve case. So it turns out the abelian variety case of the Weil conjectures, actually it's not the same as the elliptic curve case, but it follows very similar lines. You have a Tate module, TL of A, where A is your abelian variety, and you can work with that. So you can do the abelian variety case, and then they use these Jacobians, these abelian varieties, to deduce the case of curves. So at this point in the story, that's what we have. We can do curves, and we can do these projective varieties with group structure, these abelian varieties. We can't do anything else. The real barrier is finding the appropriate vector space with the nice properties. Once we have that, the analog of the Tate module, then we would have a chance of doing this. So that's what we're going to talk about. We're going to talk about associating vector spaces with geometric objects and what sort of data they can track for us. All right, so that's where I'm going to go next. But before I do, are there any questions about this summary of the sort of story and examples so far?
So Angus, you posed the question that to what extent is the elliptic curve determined by the point count?
Yeah.
Yeah, so did you want to make some comments about that?
Oh, we could discuss this now. So it turns out you can have 2 non-isomorphic elliptic curves that have the same zeta function. That is possible. 2 non-isomorphic elliptic curves can have the same point counts. And if they have the same point count on the base field, they will have the same point count over every field. But they still needn't be isomorphic. That can happen.
Over every finite field?
Yes, because as soon as they have the same zeta function, they have the same point count over every, well, because they're defined over a particular finite field, so you can look at their points over any extension of that.
No, but I
And
mean, like, if you start, can we have something over Z? Well, you have to throw away finally many things, right? But
so
can
you're
you,
asking if I have an elliptic curve now, maybe in characteristic 0 over Z or over Q, and I look at its reductions. Is
yeah.
that what the question is? Yeah, that's a good question as well. That's a more involved question. But if you start over a finite field, you have two elliptic curves defined over finite fields, then if they have the same zeta function, it turns out we say they're isogynous. There exists an isogeny from one to the other. And the way we talked about those last time, isogenies are certain maps between elliptic curves that preserve the group structure and are nice. So if they have the same zeta function, there exists an isogeny between them, which might not sound like much, just there exists a map, but it turns out that's pretty strong. Curves having a map between them.
Isogeny is like almost an isomorphism, right? That's
in a way, yeah. So it turns
like,
out
just not up to a finite thing, it's an isomorphism. So
exactly right. Yeah, exactly right. It's surjective and it has some sort of nice finite kernel. And in particular, if you have an isogeny from one curve to another, one elliptic curve to another, there exists another isogeny going in the reverse direction. But it's not an inverse, it can't be because it's not an injective map. But their composition turns out to just be the multiplication by some n map on the elliptic curve. So they're not inverse. So you don't have an isomorphism of curves, but as you say, it's an isomorphism sort of up to a finite factor. So having these maps between elliptic curves is very powerful. So that's what happens if the two elliptic curves are defined over a finite field. If they're defined in characteristic 0 over something like Q or Z, where there are lots of different primes you could reduce to, it is still the case that if when you reduced it and then took its zeta function, if those were the same at all but finitely many primes, then the curves upstairs would actually be isogynous.
but they don't have to be isomorphic?
No, don't have to be isomorphic. Again,
so there's examples even over Q, right?
Yeah.
What about, if you remember not just the number of points, but the whole Tate module that you talked about?
Good question. Is that enough? So
that's sort of the impression that I have, that's what essentially Tate conjecture says, that somehow Tate module is enough to classify your elliptic curve. I mean, in this case, it's not a conjecture. It was actually
yes, exactly.
by Tate, but I don't know if this, what exactly the statement was.
Yeah, no, that is right. So this is actually where it becomes important. I sort of mentioned that, like, for the purpose of proving like stuff about point counts, it's kind of easy enough to work with this vector space rather than this module. And this module is like a lattice in the vector space. That lattice inside the vector space is kind of like the data that determines the elliptic curve, analogously to how over the complex numbers, all the elliptic curves live inside, they're all quotients of the complex numbers, but they're quotients by different lattices. So it's a similar story. You have a lattice that determines your curve inside some vector space. So all of the elliptic curves have, if they're isogynous, they have the same rational Tate module, we call it, this VLE. So that's the same as long as they're isogynous. But if you want to be isomorphic, then yes, you actually need to have an isomorphism between the integral Tate modules. That is correct. That is
also
essentially
preserves the Galois action.
Exactly right. Yes, it has to be a Galois equivariant map. Because there is one thing we didn't talk about a lot is how these modules, these Tate modules, because of this sort of nice fact that maps on E induce maps on Tate module, in particular, the Galois action on E gives you maps from E to itself. And so that induces a bunch of maps on the Tate module. Hence, we get an action of our Galois group of whatever field we're working over on our Tate module, i.e. a Galois representation. And that's a really, really powerful thing to have access to. So that's one reason that a lot of people like Tate modules. They give you a good example of Galois representations. And yes, that is important data in this case. If you want two elliptic curves to be isomorphic and you want to detect that via the Tate modules, you have to have a map between them as Galois representations. If you have such a map, an isomorphism of Galois representations, then the original elliptic curves themselves are isomorphic.
Yeah, so this is another indication why this vector space is so fundamental, because, well, together with this natural symmetry, which is the Galois action, it completely determines the elliptic curve.
Yes.
So, in other words, it's a linearization of the elliptic curve.
Sure.
This is a linear object associated to the elliptic curve, which completely determines it. So that's sort of very powerful.
Absolutely.
So that's first remark. The second remark is that even though it's a linearization, it's still pretty difficult. However, you can compute it up to, you can compute it basically by counting points over finite field. All the information up to some finite thing is already there.
Yes.
So that's sort of where the power of the story lies. So first is linearization. So we're doing linearizing. So obviously that makes things more accessible, but not quite yet accessible enough, because then, the point is that we can actually access it using counting points.
Yes. Yes, there's a bit of a story there, how like these point counts relate to the Galois action. And we mentioned the key endomorphism that we cared about was the Frobenius endomorphism, which is an element of a Galois group, the Frobenius, you might know it as. And that is part of how all this works. The Galois action is determined by what these Frobenius elements are doing, and we know what they're doing is related to the point counts on the elliptic curve.
And that's
Absolutely.
why, by the way, if you're like, it's a bit of a surprising thing that if you look at what number theorists do, like half of the, let's say, algebraic number theories, it doesn't look like number theory at all. I mean, it's like all they're doing is like Galois representations, right? I mean, it's a bit of an exaggeration, but it's like, there's some truth. And you're like, what does this have to do with like, solving Diophantine equations? That's, but that's sort of, this is one of the first instances of the connection.
Yeah. I got into number theory, like I always say I got into it, but I sort of became enthused by it when I was very young, because amongst all the areas of mathematics, there were some like problems that were stated in number theory that I could comprehend. If someone tells me something about like, oh, this Sobolev space, something, I don't know what they're talking about. But if they say, hey, primes, they have weird patterns, I'm like, oh, great, that's cool. So I always was super motivated by number theory when I was young, because the problems made sense to me. And then you sort of start digging deeper and deeper. And yeah, at one point you're doing the Galois representation associated with automorphic forms or something bizarre. My advisor, Jared Weinstein, one time, he and I were in his office and I was talking to him about like something that I've been thinking about. And he was listening along. And at some point he just sort of slumps down in his chair and just sighs, goes, I never thought I'd be studying K3 surfaces. Never predict where anything's going to go. You always end up somewhere that you don't expect. Very good stuff. Yes, I like K3 surfaces, by the way. Good examples of all of this stuff as well. We're not going to get into them today. Okay, good thoughts. So we have this linear algebraic stuff associated with curves and a billion varieties coming from Tate modules, but we want to generalize that. So let's think to a setting where we might have seen before taking some sort of geometric object and associating with it a vector space. And that would be the theory of homology. So I'm going to give a very brief sort of summary of this stuff. If you're like me, you learned this out of Hatcher, and so you might be sort of brainwashed into the formalism of CW complexes, invented by Charles Whitehead, but certainly not named after him. No, it's not that. CW is just a huge coincidence. So singular homology is this method that takes in, say, a manifold and spits out a vector space. And broadly speaking, the method is, well, you triangulate that manifold using simplices. So, lines, triangles, tetrahedra, etc., as the dimension increases. And you pick a particular dimension of such simplices, and you just take a sort of formal vector space spanned by them. So you just, every single simple...
May I just say something first?
Go for it.
Something, I mean, this is how when one learns homology or cohomology, one usually, this is how one learns it. But really, what you should keep in mind is that what we're doing is linearizing the space, and there is thousands of different ways of linearizing spaces. It just so happens that all the 1,000 different ways give the same answer, essentially. Right?
That's quite remarkable.
So, and this is just one of the ways of linearization, but there's many, many other ways, right?
Yes.
So, this one just happens to be a little bit more accessible, perhaps, than the other ones. I don't know.
Yeah, yeah, it's a good point that like, and that is almost the theme of today's lecture. Where we're going is to discuss the fact that we can do similar things, but in loads and loads of other ways. And I don't know about anyone else, but this was certainly the first version of a homology or cohomology theory that I learned. And from there, well, there are just so many. I feel like it should be like a YouTuber. What's your favorite? Tell me about it in the comments. Like and subscribe. Yes, but you're quite right. There are loads and loads of ways to do this. So I'm just describing one that you might have seen before, which says you use this triangulation. You take these vector spaces associated to the simplicities of a fixed dimension, I, and then you have boundary maps going from one dimension to the lower one, just by taking any basis element here, any simplex, to the formal combination of its edges or its boundary elements. And then with some sign, there's a sign thing. You have to keep track of the orientations and stuff. And then the nth homology group is simply the kernel of one of these maps modulo the image of the one mapping into it. So first of all, this is well defined. The image does lie inside the kernel. And this gives you an interesting collection of things. And what it's measuring is the extent to which things that are sort of closed off, things whose boundary maps back around to itself, are or are not themselves the boundaries of other things. So for instance, here is a picture of a torus and a picture of some of these elements of the first homology group. So these are elements that are one-dimensional simplices whose boundary is zeros in that kernel, because if you look at the boundary of a simplex, it's like the endpoints of the line, and they map to it. It maps around to itself, so the endpoints cancel out to zero. And you notice that A and B are not themselves the boundary of any two-dimensional thing. There's no two-dimensional object who's inside the torus whose boundary gives you A and B. So these are non-trivial elements of the homology. And in fact, they generate it. C, on the other hand, is an example of something that's actually zero inside the homology group, because it is the boundary of a two-dimensional sub-object of the torus. One thing that's interesting about this is that this definition implicitly depends on the triangulation, but it actually doesn't. Every different triangulation gives you the same vector spaces. So nice little theorem there. So that's singular.
Just maybe a comment here. That appears to be, I don't know, a bug or a feature, depending on how you think of it, of the cohomology theories in general. It seems to me, at least, that there's always, you have to make some extraneous choices and then prove that the result is actually independent of the choices that you made.
That does seem to come up with it, yeah.
Somehow it seems like linearization requires somehow a, extraneous choices. Like, if you were looking at, the RAM cohomology, you need that smooth structure, if you wanted to use, there's like, always seems to be some extra structure required. I don't know if there's a deeper reason for that, but it's just an interesting,
This plays even beyond like linearization, just linear algebra itself feels like you often are in a situation where you have to make some auxiliary choice that goes away. Like if you want to calculate the dimension of a space, you're like, okay, I'm going to pick a basis and then I'll count it. But the basis that I pick doesn't matter. Any basis works. This sort of thing happens a lot. And when we did elliptic curves, so it's auxiliary prime L, that didn't matter. You're right, it's really interesting. So here's kind of the thing about homology. Homology is this method that associates vector spaces to a geometric object by looking at the sub-objects inside it. We triangulate it. We look at the simplices that live inside it. Another way to phrase this is to say we're thinking about maps into our space. We have simplices, which are, you can just think of an abstract simplex of some dimension, and then you can ask for it to map into your space, and that's the simplex embedded in the space. So homology is a very natural theory as long as you can easily think about maps into a space. And this is certainly natural enough for manifolds, but it is somewhat less natural for varieties. When we talk about varieties, the way we define them in algebraic geometry, we tend not to focus as much on sort of like how to build them out of subobjects, but instead we kind of think about them in terms of their rings of functions. That turns out to be the sort of key structure associated to a variety is a ring or a sheaf of functions on that variety. So we have a setup where our geometric objects are more closely associated with the maps out of the space rather than the maps into the space. So it might be more natural, rather than try and generalize the construction of homology, to try and generalize the construction of cohomology, the dual to homology. So the construction of cohomology is a very similar sort of story for singular or simplicial cohomology. You again triangulate and take a collection of simplices of a given dimension, but now instead of taking the vector space Ti, you look at the dual vector space, call that Ci. And now, instead of having boundary maps going down one dimension, you have these sort of, I don't know, differentials going up in dimensions, because these are dual spaces. So if I have a map from one object to the next one down, I dualize, I get a map going the other direction. And once you have those, once again, you can define these cohomology groups. Now the indexing has shifted around because dk minus 1 is now mapping up inside the kernel of dk. But again, all of this works and you generate cohomology groups. And in nice settings, we would expect these vector spaces to be dual to the vector spaces that we wrote down before for homology. The construction starts with these dual spaces, it spits out dual spaces as well. It's nice.
Yeah, so just a comment.
Please.
Yeah, why do we consider cohomology and not homology? You know, it's a bit of a mystery because, you know, they're after all dual to each other, but actually cohomology is much better because maybe one way to explain that is that in cohomology, actually, we have a product. So you can multiply cohomology classes, which means that, you know, well, you have the corresponding thing in the homology also, which is coproduct. But who wants to work with coproduct? You know, that's product is are much nicer to work with than coproduct.
Agreed.
I guess that would be one sort of explanation. I mean, people also give other explanations like it has better functorial properties, etc., which I don't quite understand. But yeah, it is a bit of a mystery that, you know, cohomology just turns out to be the better thing.
Yeah.
I don't know
As
if
I said,
anybody
my
else
sort of
has comments on that. Yeah, Angus, what were you saying?
I was saying, yeah, so like the sort of heuristic reason I'm giving here for why you might consider cohomology more natural is that if you're concerned with varieties, it makes sense to build a theory around maps out of the space rather than maps into the space. Hence, cohomology is more natural than homology. But that's still just a heuristic. This is not a proof for why one is better than the other or anything.
So why is it better to consider maps out of the space?
Because varieties, if we think of them in algebraic geometry, are examples of schemes, and schemes are built out of spectra, which are associated to sort of rings of functions. Once you have a variety, you have very naturally associated a sheaf where for each open set, I have a ring of functions, and that tells me about kind of maps out of the space. But maps into space maybe is a bit fiddly to work with. Graham says cohomology gives a Hopf algebra. Yeah, Hopf algebras are really nice. So yeah, but you're right that it's not a totally. I think there's a lot to be said here that's like quite interesting. So if anyone has any further inputs on this, do let us know, because I think it's a good thing to think about. Why is one of these?
Another way of thinking about cohomology, which is useful, and so you can think like cohomology is a measurement of like usually like if you have a reasonable, say, operator or differential equation, etc., usually you have local solutions, and then you want to see if those local solutions glue to give you global solutions. And cohomology is gives you abstraction to this. That's so it measures how far local solutions are from gluing to give you global solutions. So that's perhaps more analytic or physical explanation of cohomology.
Yeah, absolutely. Good stuff. All right. So let's see what sort of structures we've been sort of waxing lyrical about how this cohomology has all these great features and structures. Let's see what they are. All right. I kind of wrote these slides last night. I think at some point I was going slightly insane. So I apologize if the slide titles get a bit. I was rereading the slide titles just before this, and they're a bit weird, so apologies for that, but life is pretty good. We have our cohomology theory. I've sort of been saying you can think about this for manifolds or CW complexes. I'm actually going to assume that specifically we're going to be working with complex manifolds of complex dimension D, just because that turns out to be a better sort of analogy with our story, because the complex numbers are algebraically closed. That's useful in our algebraic story. But so we'll just, you can phrase all this for real manifolds, but we'll just do it for complex manifolds. So cohomology, we take something and we spit out some vector spaces. What properties do we have? Well, a first key property is some sort of finiteness assumption. So all of these vector spaces, if it turns out if M is compact, will be finite dimensional spaces. And more so, if M is actually, it's a manifold who's determined by some polynomial equations, then in fact, these cohomology groups will vanish as soon as the sort of degree here, this J, is sufficiently high. So not only are they finite dimensional vector space, there are only finitely many of them. So that's a useful feature to have in this setting. Another feature
maybe
is
a comment that finite dimensional vector space over Q.
Yes.
That's and Q can be replaced by any field of characteristic 0.
That is true. Yes.
Well, there's also integral versions, but let's say field for yeah.
Yeah, no, yeah, absolutely right. So we could do, yeah, so that is a good thing to notice. Notice that everything we've been doing here has been over the field Q. We're looking at Q vector spaces, which is interesting because when we did elliptic curves, we had a vector space, the Tate module, but it was defined over, well, if we think of it as a vector space, the L-adic numbers, QL. And we had to choose that L. We couldn't, there's no like Q vector space associated with the Tate module. You can't do a sort of, no, the word would be somehow like, yeah, Q Tate module. It's just not a thing. So we really need to pick some other field. But in this case, in this classical case, everything can be done using Q vector spaces or even Z modules, if you like. So that's a good thing to notice at this point. Functoriality. So if I have a map between manifolds, I get a push forward and a pullback map on cohomology. For cohomology is kind of a, as we said, it's kind of a dual construction. So the natural thing maybe is the pullback map, but you can also construct a push forward. Using this Poincare duality that we'll mention in a moment. So you get maps. In fact, not only do you get maps, you can compose these maps. You can compose the push forward and the pullback, and they give you nice things relating to the so-called degree of the map F. Another fantastic theorem in the case of classical cohomology is the Lefschetz trace formula. This is a very special theorem, and it tells us that if I have any map from a continuous map from a manifold to itself, which has sort of some niceness assumption on the fixed points. So there is something to be checked here that I'm not sort of spelling out, but assume the fixed points are appropriately nice. In particular, we can count them. Then the number of fixed points is given by this formula here, this sum of, this alternating sum, so adding and then subtracting, adding, subtracting, the trace of these induced maps, these pullback maps of F on these cohomology groups. So this is a way to calculate the fixed points of any function, the Lefschetz trace formula. And notice that if we were in this variety setting, this sum is actually finite. These vanish after a certain point, so this infinite sum is actually a finite sum. That's the case in many examples. But this gives us a method to calculate the fixed points using, so we have some sort of property of our manifold, something that we want to calculate, and we can deduce this property just by knowing stuff about what's happening on our linear algebra, on our cohomology groups. So that's the Lefschetz trace formula. And the final interesting piece, well, it's not the final, there are loads of pieces here, but the final one we're going to mention today is Poincare duality, which says two things. So first of all, the 2D cohomology group is just one-dimensional, and not only is it one-dimensional, it's like specific canonical isomorphism with Q. That is to say, there's an element in here that we send to 1. That is sort of determined. So, that's useful. And further, if I have any n, nope, this should be a k. I apologize, that should be a k. For any k, we have a perfect pairing between these cohomology groups. So HK is dual to H2D minus K. So perfect pairing means that we have an inner product that makes one of these the dual of the other. So this duality is really important. And it lets us know that...
Angus, are you assuming M is compact everywhere?
Yes, yeah, I would need to assume compact for this. You're quite right. Yes. I should probably... Some assumptions should probably be in the preamble paragraph rather than inside some of these bullet points, because we're kind of imagining them a lot of the time anyway.
By the way, this left chest trace formula is a generalization of a more familiar thing, which is the Brouwer fixed point here.
That's quite right, yeah.
That, if you have a map from disk to itself, it has a fixed point. Sometimes known as, it has connection to the Harry-Ball theorem, etc.
Yeah.
Which, a lot of people know about. But the left chest trace formula itself, I guess, is not as widely known somehow as the Brouwer fixed points or as the...
Yeah, it is a more technical result. You kind of need a bit more to say it, but it is a generalization. It specializes to those things and it is very powerful. It just mentioned the Harry-Ball theorem, and I learned the Harry-Ball theorem from Craig Hodgson at Melbourne University. Great guy, and he's very friendly, very soft-spoken, and he gave this lecture on the Harry-Ball theorem, and he sort of states it and states like, oh yeah, if you have this like ball covered in hair, then it has to be sort of tufted or a crown or something. And then after stating it, he just sort of turns to us, looks at the class and says, of course, it only works if the ball is completely covered in hair, and just pats his bald spot. Just completely unexpected from him. It was so good. This happened so many years ago and I've not forgotten it. All right. So yeah, so the left chest trace formula, if it looks a bit weird and technical, it does have many shadows that are more familiar. Good. All right. So as I mentioned, there are lots more properties of cohomology, many more that are actually specifically useful for us as well. But these are the key ones that I want to focus on.
Maybe I make another comment.
Please.
Is that, you can, well, I want to say something. I don't know if it's actually true, but let's actually say it and then see. I mean, okay. I wanted to say that this third one is also weird, a bit weird, the left chest trace formula, because it really forces your vector space to be over a field of characteristics 0. Because, you could imagine instead of looking at HKMQ, you could look at HKM with coefficients in a finite field.
Sure.
And you could imagine that all the 3 other properties, finiteness, punctoriality, and Poincare duality would hold, but there's no way this could hold, because here you're actually, you have to sum traces, and you have to sum these traces in some field. And if your field has characteristic 0, characteristic P, then you can sum a bunch of non-zero things and get 0, which is not good, right? So your trace can become 0, even if you're working with highly non-trivial things, which is not something that we want to happen. So this left chest trace formula fails if you take positive characteristic for your coefficients of your cohomology, whereas everything else, I think, can hold with the appropriate definition.
Yes, that is a very good point. Yeah, and you might even like a priori, if you just looked at this, you might say, well, the right-hand side is some rational, and the left-hand side is some integer. So maybe there's something to say about the right-hand side is actually an integer as well. But you're right, the cohomology can be defined over all sorts of different coefficient rings. But for the left chest trace formula, we need something where these traces, which are elements of whatever field or ring you've defined over, have to sum up to an integer. So that has to be able to make sense. Good. Anything else to say? Oh, the one other thing I want to say at this point is that this should feel very analogous to what we did with elliptic curves for finite fields. We associate with them some nice finite dimensional, in this case, two-dimensional vector space. The maps on the elliptic curves, induced maps and operators on the vector spaces. We had a relationship between some sort of trace and the fixed points of certain map. That was the Frobenius. And we had a pairing that was really important. So all of these things we have seen useful for us before. But we don't have at least at this stage, we haven't yet given you a cohomology theory for varieties of finite fields. We're just sort of saying, well, elliptic curves have some vector space. In characteristic zero, we have all these cool cohomology theories. So could there be a cohomology theory for varieties in positive characteristic that has these properties? Before I answer that question, let's just see how much that would buy us. What would we get if we knew just a priori there exists some cohomology theory for varieties over finite fields?
So just for a moment, if you can go
Please.
back to previous slide, people knew before, well, Grothendieck, that so there did exist and many cohomology theories for varieties over characteristic P. The trouble was that all these cohomologies that were known had coefficients also in characteristic P. Right? So imagine your M is over FP. People had various ways of defining very nice cohomology theories, but that were also over the same field.
Yes.
And they could prove functoriality, finiteness, Poincare duality, all those nice things. But there was no version of the fixed point, Lefschetz theorem, because things were in characteristic P. So that was the big missing piece. So that's the first comment. Second comment is that, by the way, because they knew how to define cohomology theories, so they also knew how to define Euler characteristic. So as the alternative sum of cohomology theories, and it just turns out that this actually gives you the right. As we said before, no matter what cohomology theory you define, it always has the same dimension magically.
Yes.
So if you start with something over Z and then reduce it to get something over C, compute your favorite cohomology, and then reduce it over FP, compute your favorite cohomology, they have the same dimension. And so the notion of Euler characteristic makes sense.
Truly magical.
Any variety. And people like Andre Weil knew about this in the 1940s. So that's why when you look at Andre Weil's paper, this Euler characteristic that appears there is, they already knew what it was. They already knew cohomology for algebraic variety. The only problem was this wasn't the right cohomology for getting the Lefschetz trace formula.
Yeah, that's a really good point. Yeah, thank you. So historically there exist cohomology theories. For us, we're gonna just at this point imagine that there existed a cohomology theory with some sort of characteristic zero coefficient that had all of these properties. We have all of these things being true. And we will see what follows from that. So imagine that we had such a cohomology theory. So we have a cohomology. I'm going to be sort of a little bit, I'm going to avoid writing comma Q or comma any particular field here to say this is some vector space. It's over some field of characteristic zero, and all of the previous properties hold. So we have finiteness, we have functoriality, we have Poincare duality, and key, we have the Lefschetz trace formula. So traces, fixed points of maps are related to alternating sums of traces. And we will fix D to be the dimension of the variety. So remember that we talked about the Frobenius endomorphism of elliptic curves. This can in fact be defined for any variety defined over FQ. This is determined by some polynomial equations whose coefficients are in FQ. And so the Frobenius endomorphism, I take the coordinates and raise to the power of Q. There are more careful ways to define this, but we'll just say this, is well defined because if xi is a solution to the defining equations, then xi to the q, you can just sort of expand it out using all the nice features of raising to the power of p and characteristic p, and see that this will also be a solution to those equations. So this map makes sense for any variety in positive characteristic. And we also know that if we want to see the set of points over any finite field fq to the n, that's given by the fixed points of the nth iterate of this Frobenius map. So if I have a point that's defined over a priori the algebraic closure, and I apply the Frobenius n times to it, and I get it's equal to itself after n operations of the Frobenius, and that tells me that x must actually have coordinates in fq to the n. It's an fq to the n point. Further, we are now in this world, we're assuming that we have some nice cohomology theory. Given this map from X to itself, we have some induced maps on the cohomology. There's some operators in cohomology, a push forward and a pull back. And I mentioned that there's this nice relationship if you compose those two things together. And in this case, what you get is that if I take the pullback and then apply the push forward maps, that gives me some endomorphism. That endomorphism just turns out to be multiplication by Q to the D, i.e. the dimension of X. So as I said, it's really some sort of idea of a degree of the map. In particular, you can, if you want, you can track through all of this for D equals 1 and think about cases that we've talked about before, like curves. That'd be a thing to do. But this is for general varieties. So let's see what else we get. So we've got this. We have some induced maps on some vector spaces. Now, let's take a look at this Lefschetz fixed point formula. So the point is that we're interested, in our Weil conjectures, in our zeta function. So we want to count the FQ to the n points of X, which is equal. I realize my notation's a little funky. I think I wrote fix in the previous slide to mean the set. I want fix to be the cardinality of the set, but whatever. You could put a dash here if you want fix to be the set. But whatever. This is some number. So it's the number of points over FQ to the n, and the Lefschetz fixed point formula tells us that's this alternating sum of the traces of those maps on cohomology. And because this has our finiteness theorem tells us this sum only goes up to 2D. So this is an expression for the point count over any FQ to the n. And these are what we're going to plug in to our zeta function. Now, we will do one trick. We are still, at some point, we've got a zeta function, which is an infinite sum. We want to take that and turn it into some rational function. And there's this sort of formal identity of matrices, which says that if I have some matrix M, then the logarithm of the determinant of 1 minus Tm, sort of the logarithm of the characteristic polynomial, if you like, is negative this infinite sum of the powers of this sort of power series in terms of the traces of the powers of that matrix. So this is something that one can, expand both sides and see that everything is agreeing with what you expect. But for us, we'll just say, okay, here's some identity that holds true for any matrix. I can relate this determinant to this infinite sum of traces. Now let's see what happens when we calculate our zeta function. So the zeta function of X is the exponential of this generating function for the point counts. But the point count we now know is this alternating sum of these traces. So I have inside this coefficient just turns into a sum. I'll factor that out, and because it's an exponential, that'll turn to a product on the outside. So it's a product from k equals 0 to 2d of the exponential now of t to the n over n times these terms, these trace terms. And this negative 1 to the k in the exponential comes out into a power. So it's each of these, k from 0 to 2d, each of those terms has an exponent of minus 1 to the k. And now we apply our formal identity. So we have to pull out an extra and minus sign. So we're going to get a minus 1 in the exponent again for this minus in front of the infinite series here. But this is exactly the right shape of thing. It's a trace of some nth power of an operator acting on some fixed vector space. Remember, the k is fixed inside this. This is sum over n. So this k is fixed. This is always the same vector space. So the same matrix, if you like. This is exactly this type of infinite sum. So this is logarithm of the determinants, cancel out exponential logarithm. And so our zeta function has now been simplified to this product of determinants with these alternating minus 1s in the exponent. So if we think about that for a second, if k equals 0, this is all of this to the power of minus 1. i.e., associated with h0, I get a factor in the denominator. With h1, I get a factor in the numerator. h2 in the denominator. h3 numerator. h4 denominator. So it seems like these hk's and these characteristic polynomials of Frobenius are exactly, at least sort of, loosely numerically, lining up with these polynomial factors we expect to see in our zeta function. Numerator and denominator of our rational function. And remember further that we were told that if our variety is sort of the reduction of something in characteristic zero, the dimensions of the degrees of those polynomials should equal the Betti numbers, the dimensions of the cohomology in characteristic zero. So if you believe, I guess I didn't say this is one of our sort of key things, but if you believe there's some sort of comparison theorem, which as Masood is saying, there always is one, all the cohomologies have the same dimension, then whatever this cohomology theory is, it's spitting out vector spaces of the same dimension as the singular cohomology upstairs. So these characteristic polynomials are exactly degree equal to the dimension of the cohomology. So these degrees of polynomials are the Betti numbers, exactly as we would hope. So the rationality of the zeta function and the relationship with the Betti numbers is just a formal consequence of having some cohomology theory with a Lefschetz fixed point formula. More is true. It keeps going. One might want to know about the functional equation as well. That was another one of our key Weil conjectures. We expect something like this to be true. So chi is the Euler characteristic. And as we've said, now that we have the language of cohomology, we can calculate this Euler characteristic as the alternating sum of the dimensions of these cohomology groups over whatever field they're defined. That gives us an Euler characteristic, and so we can ask for such a functional equation to be true. This is where Poincare duality plays a role. So Poincare duality gives a duality statement between hk and h2d minus k. But that duality plays nicely with these induced operators. And it turns out we have a sort of duality between the pullback of one operator and the push forward of that operator on the other space. So Frobenius pullback on hk is equal to the eigenvalues of Frobenius push forward on h2d minus k. But Frobenius push forward composed with Frobenius pullback is always q to the d. So what we deduce is that if I have the eigenvalues of the Frobenius pullback on hk being alpha 1 through alpha s, and the eigenvalues of Frobenius pullback on h2d minus k, brackets x, that got dropped somehow, are precisely qd divided by each of those eigenvalues. It's the same alpha 1 through alpha s, we're just taking qd and divided by that. And because I'm capricious like that, I will leave it to you to check that knowing this information precisely spits out this functional equation. Use the expression from before that we have for our zeta function as a sort of product of characteristic polynomials, as alternating products of characteristic polynomials, some in the numerator, some in the denominator. And check that knowing this plus that exactly spits out this term here, this functional equation. So, by knowing we had some cohomology theory with characteristic zero coefficients that had these nice properties of the dimensionality, the functoriality, the Poincare duality, the Lefschetz fixed point formula, many of the Weil conjectures just immediately follow from the existence of that cohomology theory. We got the rationality, we got the functional equation, we got the relationship with the Betti numbers, all that just fell out. So, the burning question is, does there exist such a cohomology theory? Does there exist a cohomology theory with those products, with those properties? Cohomology theories with such properties are referred to as Weil cohomology theories. Now, if you look at the definition, it's very technical and has lots of sort of different elements to it. But a Weil cohomology theory is some association of vector spaces to our geometric object, our variety, where these vector spaces are defined over some field of characteristic zero, and they have things like a finiteness theorem. There's some sort of functoriality statement. There's a Lefschetz fixed point formula, or a Lefschetz trace formula, however you call it. You have a Poincare duality. And there are more properties that a Weil cohomology theory is required to satisfy that we haven't used, but turn out to be very useful generally. So a Knuth formula. This is a formula that tells you what happens if I have a product of two spaces. If I have x times y, what does their cohomology look like? A cycle class map, which says, okay, if I have certain types of subvarieties, did induce classes on cohomology somehow? Which again feels like something that we would expect to be true from the classical case. We know that homology is built out of subobjects, it's built out of simplicity. So maybe subvarieties somehow give us classes in cohomology. And there are a bunch of other assumptions that one actually writes out carefully when one's defining such things properly. But the point is, it's a cohomology theory with a bunch of good properties. And should a Weil cohomology theory for varieties of finite fields exist, then many of the Weil conjectures just fall out. And it turns out there are many Weil cohomology theories. Hooray! So here are some examples of Weil cohomology theories. So the first two Weil cohomology theories are examples in characteristic 0. So not what we need for the Weil conjectures, but nonetheless, they satisfy all the axioms. So the first one is singular cohomology. That makes sense for varieties over the complex numbers. And this gives us vector spaces over Q, which have properties that we listed. Similarly, for varieties over in characteristic 0, we can compute the Durand cohomology, which again gives us characteristic 0 vector spaces, turns out of the same dimension all the time, which have the properties that you want. In characteristic P, perhaps some of the most famous example would be the L-adic et al. Cohomology. So et al. Cohomology is some general machine that can take anything, some sort of bundle or sheaf on a space, and associate to it some vector spaces and cohomology groups. In particular, there's a method where, given a space X in some positive characteristic, or any characteristic, but in particular, positive characteristic, the one that we like, and if you pick some auxiliary prime, again, auxiliary prime, L that's different from the characteristic, if there is a characteristic, a non-zero characteristic, then you can construct these et al. Cohomology vector spaces. And if this whole choice of L thing seems familiar to you, then it turns out the et al. Cohomology of an elliptic curve is very closely related to the Tate module. They are, in fact, dual Galois representations. So marvel at the interconnectedness of all things. You really can't get away from it. These are essentially, the Tate module can almost be seen as like a sort of special case of et al. Cohomology, even though the definition is wildly different, just works out to be the same thing. One other example that we won't get very deep into is the crystalline cohomology. So if you have a characteristic P variety, there's a way to build something that lives over a field more like QP, something that has some sort of p-adic topology on it. And that's called the crystalline cohomology. So you have a field in characteristic P, you can take the ring of Witt vectors of that field, you can invert P to make a field. And so this is some characteristic 0 field with some sort of p-adic topology, and you can create vector spaces over that. Oh, good question in the chat. You briefly mentioned line bundles for varieties. Is there a bundle-oriented cohomology theory which works? I'm also thinking about how powerful K theory tends to be. I'm not sure what you mean by a bundle-oriented cohomology theory. In the sense that, like, there are many cohomology theories that take as input not just the underlying space X, but also a choice of sheaf on that space and compute a cohomology group of that sheaf on that space. And et al. Cohomology certainly does that. You have to basically pick a special type of sheaf to get this sort of what looks like a sort of constant coefficient, just a QL here. But in general, you get something associated to a sheaf, and that does work. So if that's not what you're looking for, do ask again. But if what you meant was a cohomology theory that takes as input some bundle, then yes, et al. Cohomology is a great theory for doing that. All right. So there exist Weil cohomologies. Many of the Weil conjectures follow from these. I ruminated quite a while on, like, given this is most likely going to be the last lecture, what sort of note I wanted to end this on, what sort of the energy that I wanted this seminar to end on. So I thought I'd end by sort of just addressing the questions at this point in the story that seem the most sort of natural, the most on the tip of our tongues. So the first question: can all these cohomology theories be explicitly defined and worked, that's not good grammar, worked with? Can you actually sort of work out examples? Can you see what sort of vector spaces you get in a practical manner? And the answer is yes. Practicality might be a sort of sore point. You might have qualms about that depending on how deep you go. But all these cohomology theories are, very carefully defined, and they can be worked with. You can say a lot about them. Will I show you how to do any of that? No. But you shouldn't view it as something that's like totally inaccessible. There are great references on it. And as I said, I think one of the cool things about learning the story is that it gives you motivation for learning some of these sort of technical points of algebraic geometry. Milne has a fantastic set of notes on étale cohomology. And while it does require a lot of background to get on the ground with it, you can certainly see how the story develops. And it's a cool thing to aim for if that's something that interests you. So recommend those. All right. But another big lingering question at this point, is what about the Riemann hypothesis? We haven't proven the Riemann hypothesis. That's not a formal consequence of the existence of a Weil cohomology theory, and it certainly isn't. The Riemann hypothesis requires substantially more work. And when people talk about the Weil conjectures, often what they mean by the Weil conjectures is literally just the Riemann hypothesis. When people say Deligne proved the Weil conjectures, what they mean is Deligne proved the Riemann hypothesis part. The other parts were known because these cohomology theories had been constructed. But we did not know the Riemann hypothesis. So Deligne's proof does use L-adic étale cohomology, but it's not, as I say, just a formal consequence. There's a lot of actual hard work that's done, lots of clever estimates and manipulations you have to go through. This actually is spelled out in this set of notes by Milne that I mentioned on étale cohomology. At the end, he sort of describes Deligne's proof, but it is very technical and very, very clever. So how does that proof work? Will I show you? No, that's it. That's the end. We're done. We're finished. Or are we? Thanks everyone for listening. That's all I got for you today.
Thank you, Angus. Maybe I will make a remark also that about the history. So, right. So when Weil made his conjectures, there was also he didn't write about existence of such cohomology theory, but everybody somehow knew about it. And so that's what people were expecting, that somebody will construct such cohomology to prove this. So it was a total shock that the first conjecture of Weil on rationality was proved by Dwork by completely different methods. So that's using p-adic analysis, essentially. So that was so that's the first sort of historical remark. The second is that when Grothendieck developed L-adic cohomology, so we talked about how there's many different ways of doing cohomology, and in particular for L-adic cohomology, you have to choose a prime L. And so he also envisioned a set of he wanted to unify. Why is all of these different cohomologies giving you the same answer? And he sort of thought really deeply about this and came up with sort of a conjectural framework, which goes under the name of motives. And basically, this conjectural framework would explain, not only explain why all these cohomology theories give you the same answer, but also will explain the Riemann hypothesis, the Weil conjecture for varieties over finite field. So then the conventional wisdom became that one should try to prove these conjectures to then deduce the Weil conjectures. And then Deligne proved the remaining Weil conjecture by completely different methods. So bypassing these motivic worlds of Grothendieck. And interestingly, Grothendieck was not interested in this Deligne's proof. In fact, he considered Deligne's proof to be detrimental because it meant that people wouldn't work on the main thing, which was the motives. And well, anyway, people have worked on it a lot, and those conjectures of Grothendieck remain conjectures. They're called standard conjectures of algebraic geometry. And so we still, I would say, is the story is not finished yet somehow. That's because the dream of unifying in the right way all these cohomology theories is not yet realized.
Yeah, absolutely. Yeah, the theory of motives, standard conjectures. It is funny that, like, as you mentioned this, multiple times in this story, people expected the proof to rely on something, and then it sort of didn't. It's funny that was a recurring feature.
Yeah, and it's interesting that, they made all these conjectures and was deeply interested, but when Grothendieck, proved it, he was not interested in learning, and Grothendieck, spent life thinking about this, and when Deligne proved it, he was not interested in that proof. So it sort of seems to be a common theme.
Yeah. Oh, one other advertisement I want to make for the mill notes that I mentioned is at the very end of the notes. There's a little excerpt from an interview with Deligne, talking about his proof and like how the idea came to him and what he was thinking about at the time. And it is quite extraordinary that he was inspired by something wildly different, or at least at the time wildly different. If you have some knowledge of how things tie together now, the things he's talking about, you'd be like, well, of course, that's all deeply tied together. But at the time, they certainly weren't. And it took sort of Deligne to see that those two different things and realize that there was a connection between them. All right. This has been fun.